Can you hear me? Wonder if, yeah, here, let me.
I can hear you now, Tim and Ryan. Thanks.
Awesome. You can hear us. Okay. Good. All right. Thanks, Ryan. We're up and running, I guess. Okay. Hey, thanks for everybody for logging in, I guess. I don't know how many people we have on. 8 of us? Okay. All right. Hey, my name's Tim Jacobs, and I am from Amazon. I am the Director of Research Science there, and which is basically centers around optimization, applied math, and computer science for the most part. My team focuses quite a bit on algorithm development and algorithm efficient solutions to highly complex and combinatoric problems. So if you have questions, please feel to, I guess, turn on your microphone and yell, and or drop it in the chat, and we'll go from there. So let me get started here. I've got a bunch of my co-authors here on the screen. You'll see these are mainly my direct reports, that the directors that report into me that run different groups within what we call MMPROs, or the Planning, Research, and Optimization Science Organization. Nile Nguyen is a stochastics person. Phil Kaminsky is in charge of our marketplace science group. He was formerly Associate Dean at Berkeley, of Engineering at Berkeley, and joined us a 2 or 3 years ago. Ivan Oliveira came from MIT, and Xin Gao is also, she's an Amazon scholar out of Berkeley, and her area is mathematical modeling of financial problems. Scott Mason recruited him from Clemson. Stefan Karish from Boeing. So those are the main leaders that report into me for each of those. My group actually consists of 4 major areas: air science and tech, routing science, marketplace science, and sort tech science. So what that means is air science and tech is everything that deals with aircraft and air cargo. Routing science deals with the planning of the schedule, the routing of the schedule, and the operation of everything that's on the ground. So all the trucks that you see running around the system or on the highway, those are all routed by algorithms that my team developed. Then there's sort tech science. Sort tech is all the under the roof sorting algorithms that actually manage all the chute settings and so forth as we sort out packages. And lastly, marketplace science. Marketplace science does all of the pricing and revenue management across the board for all modes of transportation, and also deals with how do I price on the demand side and how do I price on the supply side as well. All right, so just to give you kind of an idea of how things work and whatnot, I've got here we go. Got a short video. I took a clip of this to toss it in here so everybody can kind of see how a package works and what happens to it as we sort through it and load it onto an aircraft. In real life, there's actual music that goes with this, but we'll forego that for today. So basically, that's just a quick capture of exactly what happens to a package as it goes through our system, for the most part. And this slide is going to give you kind of an overview of what I'm going to talk about today. So I'm going to actually go through and talk a little bit about Amazon's supply chain, from the inbound to the fulfillment centers, all the way to the delivery to your doorstep. And then talk a little bit about the breadth of OR, operations research or optimization and analytics at Amazon. Middle mile transportation, the area that we really focus a lot on, and that is Amazon Transportation Services and the science that's behind that. That's basically the MM Pros group, the Planning, Research, and Optimization Science Organization. And then I'm gonna follow up with 3 specific examples. One from surface, one from air, and one from marketplace. So two actual big areas where we actually focus a lot on within Amazon and the supply chain to get things running is what we call F2P, or fulfill to promise. So if we give you a promise that we want something that will deliver it within a day or two, if it's by 10 o'clock p.m. that second day, it should be there by 10 o'clock the next day. And that's what we actually take as a very serious deadline that we have to make. And so we spend a lot of time doing that. And when we actually make those decisions, we have a system that's called Adaptive Transportation Optimization Service, or ATROPS, which actually makes those assignments and tells us gives us what's going to be 1 day, what's going to be 2 day, what's going to be 3, 4, 5, 6 day promises. And these systems operate in real time every single day. So, and so it starts at a fulfillment center and it moves over, and I can give you kind of an idea of that entire area. But let me back up one. You can kind of see here where it starts at a fulfillment center where we keep inventory. Can go to an airport gateway or can go out onto the road directly. And then eventually ends up at a sort center, at a delivery station, and then to your house or to a locker system. I think, you guys have locker systems here? You have the Amazon locker system? Is there? Okay, yeah. So that's kind of a very interesting problem in and of itself, but that's one of our delivery mechanisms. So if you take a look at the examples of how we actually use OR and ML, specifically, if you think about just linear programming, dynamic programming, integer programming, and so forth, those are great methods, but problem is the problems that we solve are so big, they become very cumbersome to solve, and it takes a long time to solve them, right? And so what we've actually started transitioning into is making combinations of your traditional mathematical optimization plus ML, machine learning, reinforcement learning, or AI to actually help move things along faster. And where we also use those areas are within labor scheduling, for how do I schedule aircraft crew, how do I schedule truck drivers, and so forth. Maritime transport, we actually have 2 areas, 2 or 3 areas actually, that we actually transport things by over the sea. That is like Northern Ireland to the Netherlands, also from China into the United States. Rail transportation, specifically in Europe, India, and also some here in the US. And then demand forecasting, how do we, helps us if we have good input into our models and so forth. And automated buying and inventory management. This is a lot of the things that my team does quite a bit of, all the way down to the last thing. We have a whole group of engineers that work on nothing but robotics that actually run the fulfillment system. So, which is kind of interesting. One of the largest stations within Amazon's network is in Cincinnati, and that is the Air Hub. And you can, if you ever get the chance to go there and see it, it's huge, and the entire sorting floor is robotic. So, okay, middle mile actually looks at, we do about 100 million packages a week. They get moved, running about 20 to 30,000 daily truckloads and 250 daily flights worldwide. And that is expanding. We're actually growing that part of the business quite a bit. And you can actually see a number of areas. This this picture here is actually from Cincinnati. I took that when I was up on the tower, looking down and trying to get, as we were trying to get the station up and running. So, but that's what middle mile is. Middle mile is not the delivery truck that brings it directly to your house. And it's not the management of the fulfillment centers of the sortation. This is our actual total supply chain, as I showed you earlier, that moves things across from fulfillment centers. And we actually have an inbound network into the fulfillment centers that we actually run that supplies inventory. Now, one of the things that's interesting is you think about a fulfillment center being nice and organized and a place where you would, hey, I need a hammer, I need a screwdriver, I need, wrapping paper for Christmas or whatever. And it's all in a certain spot. And that's not the way we do it, actually, because these buildings are so big. But what we do is we have everything scanned and we put it randomly across the floor. So that because the probability is you're going through the list of things that somebody might buy, the probability of the hammer or the screwdriver being near you, one of them, is much higher than having to walk all the way across the other corner of the building. So that's exactly how we actually organize the FCs, and it works really well. So given that, if you look at just the transportation side of it, that takes stuff from the fulfillment center to a sortation center or a delivery station, one of the two. That's the whole, all that network in between is what we're actually running. And again, more than 100 million packages in just North America. And you can kind of see a little bit here from this chart. This is our flight network. That's a little dated at this point, but it didn't update it. And one of our real focuses right now, the scale of these problems is huge. And I'll get into that here in a minute. But so our focus to actually solve these is to look at using ML and AI combined with optimization-based decision-making to get problems and get solutions that are good quickly. So customers don't want to wait for 15 minutes to see the price of an item or the price of shipping an entire load of something. They don't want to wait 15, 20 minutes. We need it in 5 seconds or less. So that's the kind of thing we're actually doing. And we also look at what we call prescriptive analytics, where we actually go back and actually see, are there problems? Is there a feedback loop that's missing that we need to add in to get the system to work better? Okay. So given that, we do a combination of optimization, machine learning, and meta-heuristics. So meta-heuristics are things like local search or iterated local search, where you search around an area for an optimal solution or a good solution, and then you kind of use some probabilistic perturbation to jump out of that area and look in another area of the decision space and get a good solution. And by combining these three techniques or a number of tools from these three techniques, we can actually get an efficient, a connected, and a flexible schedule. So just to give you kind of an idea of what we're looking at, this chart here is a rendering of our trucking network, and it's just straight lines for connecting. While this is an animation of the actual air network. We can show you that. I can actually get that to work. We'll come back to it. Anyhow, so let's just take that air network and figure out what we're actually going to do. So this is the one of a big problem that we have. If you look at, so I said we have 250 some flights a day now. If you go back 5 years, we have 110 aircraft today. If you go back 5, 6 years, we were flying 3 airplanes. They were charters, and it was kind of, we could fit the entire organization in a conference room. Today, the organization is over 12,000 employees. My team alone has, for air alone, has on the order of 75 scientists and computer science developers and software developers, just to support that system. Okay, so let's think about what we're going to do. We're actually going to sit down and we're going to figure out where we're going to fly, what station. I've used these 3-letter IATA codes here for Ontario, California, Seattle, Cincinnati, Charlotte, and Tampa. If you ever take a quick look at your airline tickets, you'll see some of these things on there. And what we're going to do is we're going to go through and try to figure out the first step we're going to see is once we pick the stations of where we're supposed to fly, when do we do it? And then finally, what aircraft do we actually assign to each one of those flight legs, okay, or segments? And what you'll notice is there's a couple of things that have to happen here. You'll notice that Tampa has one outbound airplane and one inbound airplane. It has to balance because aircraft are very, very expensive and I can't buy one every morning or sell one every night. And so I have to have everything balanced over a 24-hour period or 48-hour period, depending on what the business model is using. And you can see, we'll find out here we have Cincinnati has an outbound and not 2 outbounds, 3 outbounds, which means that I better have 3 arrivals by the end of the day. And I sure enough, I do right down here. And so that balances the aircraft over a 24-hour period. And so this network alone for us is is about 3.8. Well, that's actually about 4.5 million fleet flight combinations that we have to decide on within our network alone, right? We're also looking at out of about 300,000 origin destination paths that are possible, we're actually going to manage about 85,000 of them, and we'll ignore the others. But we have to be able to put flow over those 85,000. And then lastly, it's about 3.8 million packages a day that transition through this network and onto trucks at the other end. So we're going to minimize our transportation operational risks, our fuel and sustainment costs, and then also maximize the efficiency, speed, resiliency, and flexibility. If I end up with something happening in the network, like a storm that shuts down Tampa, this airplane is going to get stuck somewhere, and I need a way of working my way out of that. So we actually plan that into the models that we actually solve. So if you take a look at this, looking at a lot of airlines do this manually. They sit down with a basic schedule. They tweak it a little bit here and there. They use a lot of products, like there's a product from Sabre called Flight Manager or Schedule Manager that actually allows them to manipulate flights by hand and so forth. It takes an army of people to do it. We don't do it that way. We actually wrote a program. We actually wrote an optimization algorithm along with the interface and everything called A2D that actually optimizes this. It will build from scratch a clean sheet schedule in about 30 minutes to an hour. So we can actually take that schedule and then turn it around and send it to any one of the carriers that are flying for us, or send it to our carriers and then actually have them go ahead and crew it and get ready to go. It also, at the same time, will actually estimate the amount of package flow underneath within that network. And we don't a priori prescribe connecting points. We let the model decide where the connecting points will be and how many packages should go through each one of them. So, and we do this it's just basically a multi-commodity network flow problem. And we use a reduced cost column generation approach in parts of it to help solve that problem. And in our forecast, we use a machine learning based forecasting system. The nice thing about this is in air, from operations planning, from planning all the way down to the day of ops, everything is automated. We automate the entire thing. Right now, we're catching up on a couple things like maintenance and some other things, aircraft maintenance planning and scheduling and so forth. We're adding those in. But what's interesting is that we can actually run this and get a much better schedule. In fact, one of the things that we did is by actually using this system to plan the schedule, we were able to up the load factor on each of the aircraft by about 4 or 5 points. So, which is pretty good. It's quite a bit. And people, you'll talk to airline people and they'll say, it's a form of art. No, it's not art. It's math. It's simply math. Okay, and it's math in a systematic way of approaching the problem. And you will find opportunities that you'll never find by hand. Again, you're talking about something with 4.5 million fleet flight combinations. You'll never be able to see all of those options. Okay, but let our systems and let the computer systems that we actually build do it, and it goes much better. Okay. This is one of the outputs of our system. You can kind of see this in the animation of the actual schedule running and flying. And I didn't put India in here. I did put Europe. I left out China and Asia, but I put in Europe and the US. And you can kind of see how the flights kind of blow in and blow out over the day. The color of the aircraft actually it tells us a lot. It tells us whether the airplane is, if it's green, it's on time, everything's going well. If it is red, that's a bad deal. It's late, and we can actually hold your cursor over that and find out exactly why it's late. You can find out exactly how many packages are on board, how much they weigh, how many cubic feet there are of each of them, whether or not we've had a maintenance problem, we've had a crew shortage, whether or not we've had a ground delay for weather or something like that. All that information is there. Now, you can also look at that. You can click over to this window, and you can see the actual schedule as it operates through the day in terms of each airplane that's flying. And then you can click on over that and you can get the exact same type of information about what's happening to each one of those airplanes. If you actually run your cursor over any one of the stations, you can tell what the weather's like. You can tell whether they're using instrument flight rules, visual flight rules. You can tell what their cloud base is and their horizontal visibility is for the pilot. So it tells you quite a bit about the whole system. And when things start to fall apart due to weather or something else, that's what we call the NCC, the Network Control Center. They're running this day in and day out. But this is the exact same view that the planners had 3 months ago when they actually designed the schedule. So they see it from start all the way down to finish. So from planning all the way to day of ops. Now, jumping over to the transportation on the ground, that's a little different, right? Trucks are cheaper and they're all independent contractors, right? They're independent drivers, independent companies that drive for a whole bunch of companies. And you can get a lot of trucks to show up and do something if you need to. That's what's interesting here is this is about 48,000 loads a day right now. That actually equates to about 10 to the 88 possible routes in that schedule. Okay, so that's a lot of zeros, right? So for any of you that want to actually see how big that is, you can go out and Google how many atoms there are in the visible universe. It's less, 10 to the 85th. Okay, so you can kind of, and we're not going to talk about dark matter or anything like that. This is a big number. It would take us forever to get a solution if we had to try every single one. Now, a lot of those are very myopic and naive routes, right? I'm going to drive just one direction and that's it. That's my route. It doesn't make any sense. But when I started at Amazon, I started this group and this organization to do this. It was taking the operations team 36 hours to create loads, not for 48,000. They could do 7,500 loads. It took them 36 hours to solve it. Today, we can actually solve up to 150,000. We do it in under 4 hours, top to bottom. It goes directly to each one of the carriers. They can actually get through their cell phone. And it tells them exactly what and they pull up an application that actually does their navigation for them and everything. They just have to say, okay, I can take it and I'll go. And so that's kind of the type of system that we're working at. It actually reduces our cost quite a bit by actually doing that. I think when we actually turned the routing system that we use today on, the original version of it, it dropped our cost by 7%. It's quite a bit. It's seven, yeah. It's still a pretty big number. Right? So that was kind of neat. And then so let me go through three specific areas that we can talk about. That we'll talk about very where we use these kind of tools and we build these kind of systems. First one I want to chat a little bit about is spare aircraft location and crew callouts. Okay, doesn't sound like a very exciting problem, but if you end up with an airplane on the ground, what we call an AOG, because of maintenance, it has a trickle-down effect all the way through your schedule, all day long. And it makes everything a mess by the end of the day, okay? If you have an airport closed because of weather, we end up with these problems. So we have to figure out how many spare aircraft do I need? Well, if I have 10 airplanes, I don't want to have 10 spares because it's very expensive, right? anybody, if you know what a cargo aircraft or a 767 costs, if I were to go to Boeing and buy one, it's about $137 million just to buy one of those airplanes. So we don't want to do that. So we have a very few precious spares that we have to put in place around the network so that we can get things to work. And to make sure that we have the ability to have crews to fly them. And also, if we have a maintenance problem, then we have some way of getting the crew and that airplane out and running very quickly. This is what we call an irregular operations, weather maintenance, and so forth. Support disruption recovery. We want to try to alleviate any propagation effects. These delays propagate all the way through the network. And every time one of those happens, we're delaying the delivery of a package to the customer. So we want to defend against that. And then we also want to figure out where we're going to optimally locate these airplanes so that they are the most beneficial placement along with the crew, so we can use them in short order. All right, so here's what we did. We actually went back and we looked at a stochastic programming problem. What's the probability of the plane actually breaking? Okay, what is the probability of a weather event getting in the way and actually causing a problem? And so we sat down and looked at that and modeled that. And the real brain behind this is Nile Noyangan. She is an awesome stochastic modeler. She has a very good insight into how these systems work and how we should model it. And so created this little optimization, created a little prototype to see if it would work, and it worked really well. And so now what we do is we actually optimize our schedule so that we can optimize, and we actually, the optimal solution says, here's a station. Each one of these is a station, columns is a station. Each one of these is the aircraft type that we have at that station, okay? And here is the actual window we have, window in time that we actually use for that plane to be sitting there ready to go with the crew either on site or across the street at the hotel. So, and by doing this, we've actually been able to increase our coverage quite a bit. Yeah, I thought I had that on here. I think I do on the next. Yeah. So what we actually did is by doing a mathematical optimization for it. So we looked at this and created that. It solves very quickly. It is actually done automatically through every schedule that is published. We have right along with the actual flying schedule, we have a spare schedule. And then that spare schedule goes in and we actually assign crew, captain and a first officer to each one of those aircraft for those windows. When we actually did the full adoption of this, we were able to increase our flight coverage by 7% on the origin, and by 33% without increasing the number of spare aircraft that we needed, even though we increased the amount of flying by 16% on the main schedule. So quite neat and quite good. For the peak holiday season, we reduced our spare costs by more than 7% again, 40% more flying compared to previous peak, because peak, we actually ramp up quite a bit. It's not just the 16% anymore. During the holidays in December, from about Thanksgiving through the first of the year, of the following year, that is our peak season, and we ramp everything up quite a bit. Okay. All right, so that's looking at that. So let's go back and take a look at the marketplace. Okay, so in the marketplace world, drivers, carriers for trucking companies have a series of load boards they go to, and they'll bid. They put in bids. I'll take this load from A to B. So if I say Phoenix to Tucson, I'll haul that for $700. Okay, somebody else might come in at $600, $650. And what happens at some point in time, the brokerage office calls the winning bidder and says, okay, it's yours. I'm tendering it to you. Come and get the load and go. Got to pick it up by 3:30 this afternoon, go. That's how it was always done. It's kind of a messy situation across the board. There's no way around it. It's just messy. And so what we do is we were looking at it and we would get gamed on this all the time. So you'd end up with somebody would wait, they'd wait really long, and then they'd put in a bid, and the bids would be really high, and you'd have to you had no choice, you had to take it. So instead of that, what we actually did is we created something called accept now pricing. and built out. This is one of the things that's really kind of cool. It uses Bellman's principle of a dynamic program to actually figure out all the different possible prices in the future between now and the time of departure, and says, well, here's what I'm going to actually put out on the market today. Well, that's a very combinatoric problem. It takes a long time to solve. So what we actually did is, think of it like this: is I took a machine learning approach to this and combined it with the dynamic programming problem. And it's very similar to if you're driving down the street and you see somebody mowing the lawn on the right, and you see a kid playing with a ball in the street. Your focus is on the kid with the ball in the street, right? You kind of ignore the person mowing the lawn. Probability of that impacting your transportation is very low, but you don't want to hit the child, right? And so we as humans focus in and we ignore a lot of the inputs that we get. Same idea here. Mathematically, I am going to focus on what is really pertinent to solving this problem right now, knowing that I have other time periods in the future. If I make a mistake, I'll fix it. I can go back and fix that, right, in the next time period. And so what we actually do is we put this in and we can solve it, and we solve it very, very quickly. And we can put out new prices every 15 seconds for carriers, right? There is no bidding anymore, none at all. We surface a price, you look at the price. If you're a carrier, you can be a trucking company with 1,000 trucks, you can be a trucking company with 2. Both are treated equal. If you're there and that load works for you, you click a button, it's yours. All right. And we originally paid, when we used bidding, we paid about a 55% premium over contractors. Okay, so if $1,000 load on, these are for last minute loads. In the last minute, if you're looking at last minute loads, in 24 hours down to the hour of departure, you pay this 55%. If it's $1,000 for contract, you would pay about $1,550 or so, something like that. We've been able to reduce that down to 0.74%. So which is quite good. And this is actually a thing that is now a product called Relay Load Board. Has another product that goes along with it, a sister product that is called Relay Carrier Marketplace, which actually does the same thing for your longer contracts and your short-term contracts. So we put all of that in, and it actually has done a very, very good job across the board. So it has also increased the number of carriers that we actually work with. So it's not just these huge carriers like JB Hunt anymore. It's small carriers that might be, a family operation that has 2 trucks or 4 trucks or 1 truck or whatever. They're also driving. We now run, used to be with the bidding sites, we had around 200 carriers we worked with. Today we work with 65,000. Okay. All right. Okay, so where are we going next? And so what's actually happening is every time we surface a price, you can see these are the time increments here. Every time we surface a price, it's either accepted or not accepted. And that's feedback. That feedback loop updates our overall offer rate and the likelihood, the probability of that being accepted. And so as this thing runs constantly, every single day, we collect a lot of information that gives us information about what is out there, how much supply is in a certain area of the country, where we need to up the price, where we have to pay a higher premium to get people to drive. And you can imagine, it's not a whole lot of transportation, not a whole lot of people going to North Dakota. Okay, so you pay a higher price there. But here to Tucson, maybe not. So, okay. So where are we going in the future? So I've talked a little bit about routing. I've talked a little bit about airline schedule generation and how to deal with the spares aircraft. And I've also talked a little bit about how we actually price and market in the marketplace to secure supply, like trucks and aircraft and so forth. But now the idea is, look, it's a real trade-off. There's a spinning wheel here between price, demand, and supply. And what we can actually do is we can actually look at that to dynamically match supply to demand in real time. And by doing that, we can actually lower the costs. We have make promise with the reliability, a very high reliability. We get lower cost, better pricing for shippers. They get the truck drivers get a better price, better work experience for the carriers, and then there's less risk, more flexibility. Because if we don't have it contracted, I can actually get it in 12 hours, or I can get it in 3 hours or 2 hours if I had to. So, and I think that's it. I'm happy to take any questions if anybody has any. Yes. Well, yeah, sometimes it's between 2 and 3. Yeah. We do it every schedule. We do it every month, has a slightly different schedule. Right. That's a lot of that's driven by the fact that you just can't move airplanes around that quickly. Number one. Number two is collective bargaining agreements for the carriers. So pilots are unionized, and they are under a collective bargaining agreement for the individual carriers that they fly for. And when they fly for us, we go by those rules. So they bid their flying for an entire month. And they do it about 45 days prior to the month starting. That's correct. Yeah. Yeah. So, and then if we want to bring an airplane on and get rid of another airplane, that takes time. You get the airplane in, you have it checked by the FAA, you actually run all your tests on it and everything before you actually fly it. If you want to deprecate an aircraft, what you're doing is, if it's a leased aircraft or you own the airframe, you've got to figure out what you're going to do with it. And then if it's, we do engines and aircraft frames separately. We don't, the aircraft engines don't stay on the airplane. We move them around as needed. Yeah, and so but that's very common. That's not just us. That's every airline on the planet like that, because engines are just expensive assets to have laying around, so forth. Yes. Yeah. Yeah. So we kind of get an idea that we're going to have a downtime. If we see the weather coming, what we will do is get those airplanes out of there as much as possible. That's very typical in like a hurricane. If you got a hurricane coming into Florida or into the New Orleans area, what you'll do is you'll move all your aircraft out as quickly as possible. If you remember, I think one of the big hurricanes that hit New Orleans many years ago, one of the things that we did there, I was with the airlines at the time, and we actually flew out all of our aircraft out of there the week prior, just to make sure that they weren't damaged. Yeah. Some airplanes that are not operable, they've got a problem, we're trying to fix them, they get hammered. But hopefully we didn't have that problem. Yeah. Yes. Yes. We are also actually the largest user of sustainable air fuel. Yes. We have an active program where we invest in SAF to operate the aircraft. And the other thing that we do too is on some of our large facilities. It's not just the footprint of the aircraft itself, right? And we have a whole lot of things running around on the ground that need power, as well as the building itself. And so what we've actually done is we've moved a lot of our ground systems to being rechargeable and electric. We've also moved and put solar panels on the top of our bigger facilities to actually run the facility, to power the facility. And that works extremely well. And then in addition to that, we have an ongoing program. In fact, my group is very involved in the design of the electric box trucks and the electric tractor trailer vehicles that we're putting together. So I spent a lot of time with one of my guys working on wind tunnel experiments and pulling out my old finite element books to look at computational fluid dynamics and work through that. So yeah, it was fun. Yeah. Yeah. You can kind of see the headlights are like a circle of lights. Yeah. So yeah. They work pretty well. No, they work pretty well. So there's two versions. There's one that they're the open road. That's what we call a box truck. And then there's the delivery van, which is, there's two sizes of those. Those are kind of the swooped ones. The box truck actually, if you looked at it, you'll see that it's got a fairing and everything that makes it very streamlined. But if you look at it from the air, it looks like an airfoil. We've actually created it. It actually tapers off to the back so that we actually bring down the vortex off the back of the truck, so that because that essentially becomes drag, right? That's exactly what it becomes. We've also put winglets on our aircraft, so yeah, so that helps. Any other questions? Is that it? Well, if not, it's okay. If somebody does have questions, talk to Ryan. He can get a hold of me, and if they're interested in Amazon overall, please let me know. But thanks for having me. 26th, I should be here in the morning. I think it's the morning. Right? Yeah, I'll be here on the 26th. Cool. Yes. Exactly. Yeah. Cool. Thanks, everybody.